Okay, good afternoon, everyone. My name is Joe Steele. I'm the Communications Director here at Lift. I want to thank everyone for joining our very first Lift Off webinar series aimed at helping small and medium-sized companies talk about their technologies a little bit. I'd like to thank our partners at Michigan Manufacturing Technology Center, the center right here in Plymouth, our manufacturing extension partnership partner here in Michigan. So thank them for helping us get this off the ground, and want to thank Optimal and Dan Radomski for being our first presenter here today to talk about technologies that enable the joining of dissimilar materials. I want to start off with a couple of housekeeping issues. The first is I want to ask everyone to please mute their phone. I will do my best to keep everyone on mute except those that need to have the floor. If you do have questions, please use the chat function that is on the GoToMeeting site, on the GoToMeeting taskbar that you see on your screen, and send the questions to the organizer. Those questions will come to me, and I will be able to facilitate them and organize them and sort through them as we go through the presentation, so we can ask Dan those questions at the end of this presentation. And finally, each Liftoff webinar will be recorded. So we're recording this particular webinar right now, and we'll post them to the Lift website later on for future viewing. So I want to go through the agenda a little bit. First of all, we will start off with a little bit about Lift for those on the phone that don't know what Lift is, as well as the center, a little bit of background on the center, and then Dan will take over to talk about the topics he's going to cover, from industry issues and what is driving lightweighting in the industry today, some of the challenges, and along with that, a couple of the technologies that he and his team have developed in researching those particular topics. We will try to save some room at the end and be respectful of everyone's time, and have some time for Q&A at the end. So first, a little bit about Lift. We are one of 14 Manufacturing USA institutes around the country. The Manufacturing USA developed institutes to reinvigorate manufacturing around the country back in 2014. We were one of the founding members of Manufacturing USA, and our mission is to accelerate the development and application of innovative lightweight metal production and manufacturing technologies to benefit both the U.S. commercial and defense markets. To do so, we have three legs of our stool that we operate in. We operate in technology development, the research and development of new lightweight solutions. We enable the technology transition. We help our member companies transition those innovative solutions into the marketplace. And then we also focus on education and workforce development. We have instituted 40 different initiatives in our initial 5-state region, running from Michigan down to Tennessee, to better prepare the workforce of the future. In terms of our technology, we operate in 6 different pillars of technology, those being melt processing, powder processing, thermomechanical processing, agile processing, coatings and corrosion, as well as joining and assembly. So all of the technology that we operate in spans the metalworking spectrum. We can work with our members in a number of different ways. We operate in shared technology projects where resources are pooled and risk is mitigated to help enable lightweight solutions that our industry members want to have hit the marketplace. We invest in the workforce of the future, as I mentioned. We provide engineering services to our members. We are in the midst of constructing a $50 million facility here in Detroit, where we will have full-scale R&D equipment, from thermomechanical processing to coatings to a machine shop, to provide all of those services that we need, that our members need to conduct their R&D work. We also bring industry and government together to help better provide lightweighting solutions, and we have a technology help desk that allows people that are in a jam to be able to contact us with the help of the center to get those questions answered right away. We also have 11 different focus areas that we focused on for education workforce development, and all of this information can be found on our website at lift.technology. You can go visit there and you can check out all of our current ongoing technology projects. You can find more information about our education workforce development initiatives. You can see more about the equipment that we have under construction here in our high bay that we're going to unveil in a couple of weeks. You can also follow us on Twitter at News from Lift, and you can also contact us at 313-309-9003. We are hopeful that this webinar series will go on well into the future. We are looking forward to highlighting many of our members going forward, and hopefully share some information, share some of their technology, and share some best practices going forward. So with that, I will hand it off to Elliot Forsythe at the center to talk a little bit about Michigan Manufacturing Technology Center.
Good morning, everyone. This is Elliot Forsythe. Thanks, Joe, for the introduction. As Joe mentioned, we are part of the National Institute of Standards and Technology. We're one of 51 organizations across the United States whose sole purpose is to focus on small to mid-sized manufacturers and help them to prosper and thrive. And to prove what we are actually able to do, in the past year, we have worked with over 400 companies, and for every dollar they've invested with us in projects, they've received a return financially of $106. So we're thrilled with that opportunity to work with small companies and to help them prosper and thrive. Our relationship with Lyft started at the very onset back in 2014. And throughout the course of time, we have had the opportunity to bring on a very talented materials engineer, Greg Peterson, who I'll turn over to in a minute. But principally, our relationship with Lyft now is to turn back to our core mission about prospering and thriving. The great technologies and products that are developed by Lyft need to be commercialized into the marketplace. And so Greg is part of the technology team at Lyft. As products and technologies commercialized, it's his role to help embed those throughout the United States into small to mid-sized companies. And so it's my pleasure to introduce to you Greg Peterson, who will introduce our speaker today. Greg, it's yours.
Thanks, Elliot. My name is Greg Peterson. I'm the embedded engineer. I work for Elliot at the Michigan Manufacturing Technology Center. I have basically an office at Lyft. I spend 100% of my time at Lyft assisting the small and medium manufacturers in advancing their understanding and technologies to assist in the lightweighting revolution that's taking place in the United States. So this webinar was set up as a means of assisting our SMEs to commercialize their technologies by giving them basically a national exposure through the center and through Lyft's connections with industry. So this is the first event, and there will be many more. At this point, I turn it back to Joe Steele.
Thank you, Elliot, and thank you, Greg. Now it's my pleasure to introduce our guest speaker for the hour, Dan Radomski, the Chief Operating Officer of Optimal Process Technologies. Dan holds 3 C-level positions with the Optimal Group of companies that includes Optimal CAE Inc., Optimal Materials, and Optimal Process Technologies, which is an innovative group of small businesses and startups focused on reverse engineering, competitive benchmarking, automotive vehicle engineering, and lightweighting technologies. Dan leads the strategy, the business development, and commercialization efforts for Optimal Process Technologies, which is a Lyft member. They've developed 2 unique lightweighting technologies, which we'll hear about today. One, a rivet weld system that has proven effective to join dissimilar materials like steel and aluminum. And a second, a weld quality assurance system that effectively measures the quality of the similar material joints, including battery cell-to-cell and cell-to-bus bar welds. Previously, Dan was Vice President of Industry and Venture Development at Next Energy, which is an energy and transportation technology incubator based here in Detroit, Michigan. Dan led the commercialization services, including the market and technology analytic efforts, and supports the growth of early stage and mature energy technology firms. So with that, I will hand it over to Dan to take it from here.
Thanks, Joe. Appreciate the opportunity to be with you today and to be a partner on delivering this this webinar focus on lightweighting. We have been a LIFT member for over a year now, and have found that it's been a great opportunity for us to network with other companies throughout a wide variety of different industries and throughout the value chain that have equal visions for lightweighting structures and have unique industry application needs where not only our technology but others can solve challenges. So appreciate it very much, the opportunity today. So a little bit about Optimal and our group of companies. We have 3 companies and established vehicle design and engineering firm that's been around quite a while as a tier 1 supplier supporting vehicle development, structural optimization, lightweighting. We have offices all over the world. We've been involved in electrification and lightweighting as one of our primary capabilities. So about that, Optimal, as I mentioned, is a group of companies, established vehicle design and engineering firm. We also have 2 technology startup companies, Optimal Materials, which is focused on advanced materials, including lightweight materials like bamboo composites, and then Optimal Process Technologies, which is primarily focused on advanced manufacturing processes that support lightweighting and electrification initiatives. OPT is the company that is a LIFT member, and today I'll be presenting with our Chief Technologist, Dr. Tae Kim. We have a wide variety of customers in the automotive market as well as in other industries. So let's talk a little bit about, what is really driving lightweighting. Regardless of what industry you're in, especially in transportation forms of all type, fuel economy and emission reduction requirements are really driving the need for lightweighting. In aerospace and other industries, we are operating fleets of vehicles like aircraft. Fuel savings that enable lower operating costs are driving the need to look at lightweighting solutions to improve those measures. The major drivers for those that are OEMs that are actually designing, developing, and selling transportation devices, whether it's automobiles, aircraft, Navy ships, agricultural equipment, are government regulations. And we're seeing it at all levels, whether it be CO2 emission reduction requirements that are in fuel economy improvement requirements that are either at the federal, state level, as well as regional and local encouragements. So here's an example. In the U.S., most of you already know this, but the CAFE, or corporate average fuel economy requirements, are driving automotive vehicles, passenger vehicles, and light-duty trucks in the U.S. market up to standards of 54.5 miles per gallon across their entire fleet of vehicles that they're selling. There's also a number of other things driving adoption of fuel economy improvements, efficiency at the federal level for a wide variety of different industries. At the state level, you're also seeing very aggressive measures. California, New York, and other states that have clean truck vouchers and other things are in minimum incentives for OEMs and those that buy those vehicles to adopt about transportation industry, anything that consumes fuel and creates emissions, CO2 or otherwise. So we tend to think of the automotive industry as being the main driver because of the regulations, including the ones I shared with you. But as you get into commercial vehicle trucks, there's similar initiatives and activities driving this, even in the military and defense vehicles, off-road vehicles, 2-3-wheel vehicles, and obviously in other industries like aerospace, marine, and rail, where the entire industry is focusing on lightweighting as one measure of supporting fuel reduction and emission reduction. Aerospace, for instance, has a number of approaches. Lightweighting is a big initiative on the actual structures, but there's also other ways to get at fuel consumption reduction targets and emission reduction targets, including improved aerodynamic designs and more efficient turbine engines in the case of aerospace. In automotive, it's a multi-pronged approach, including electrification, and that's not just full battery electric vehicles, but hybrid vehicles, micro-hybrid vehicles. Obviously, lightweighting structures, including especially the body in white and body closures, are a key initiative. But there's also other approaches, including just more fuel-efficient engines, transmission systems, turbochargers, downsizing engines to like 2-stroke engines in combination with a micro-hybrid battery. Many different ways the OEMs are approaching this, and not only in the U.S., but abroad, to bring about opportunities. Is among the most important and popular strategies for reaching these goals. This is a chart that kind of shows among a number of measures and surveying a number of automotive OEMs, the approaches that they're using and focusing on to bring about better fuel economy, and specifically, in this case, in automotive, reaching the 2020 CAFE requirements, as mentioned earlier. As you move in this direction of lightweighting, one of the most popular approaches is obviously going to lighter weight materials. In most cases, you're finding that automotive OEMs are still in need of steels and high strength steels in certain areas of the vehicle, especially on the body in white, the structural domain of the vehicle, as those areas like the B-pillar and other sections really are pretty important to be very high strength to support crash and safety standards. And then some areas where you're working with semi-structural components, in other areas, they're moving towards aluminums, magnesium materials, even carbon fiber and other polymers. And why are they moving in this direction? Because use the appropriate materials in the appropriate locations of the vehicle and still being able to get at some of this lightweighting initiative. Being able to save weight, you know, this is a look at our company, Optimal, also does benchmarking on vehicles to appreciate the value of how vehicles are being designed. This is an example of 3 hoods of vehicles that, roofs of vehicles for 3 different sedans that we looked at. That primarily use steel, and we were looking at the opportunity to try to lightweight these structures by moving to aluminum. So you can see here the weight savings that are given as a potential if you're able to switch out to aluminum while still maintaining the strength and durability that structure needs to hold in its operating environment. It's significant. The challenge being, when you have a mixed material strategy and you have, in this case, an aluminum roof, you have to join that aluminum roof generally to a high-strength steel. Facial bonding between the materials is often brittle and can fail and propagate to a failure over time. And obviously, galvanic reactions of different materials causes corrosion, as you can see here in this photo. So for all these reasons, joining dissimilar materials methods have not been necessarily proven to be very durable, especially in a harsh environment, product like an automobile, where you have, it needs to operate in hot, cold, wet environments, vibration, and it's a challenge. So, just to give you an idea, we will talk a little bit about optimum process technologies and one of the technology solutions, a couple of the technology solutions that we're developing to address this problem. However, I wanted to make sure that everybody was aware that there's a wide variety of industry players, academic institutions, all over the world, not just in the U.S., that are focused on trying to solve this problem. And there's many different approaches for different alloy joining that are being addressed for very specific industry applications. So what you see here is the findings from a research study that was conducted in partnership with Optimal Process Technologies, LIFT organization, and the center, Michigan Manufacturing Tech Center. And what we did is we looked at all the joining of dissimilar materials technologies that were at least public and out there and funded, or that companies put out press releases about. And as you'll see here, there's technologies that are addressing not only aluminum and steel, as I mentioned, but dissimilar aluminum alloys, like joining a 5000 to a 6000 series of aluminum. Obviously, and steel is the other materials, aluminum and magnesium, and steel to cast iron. So many of these are your traditional joining processes, riveting, welding, in some cases a combination of different technologies, including structural adhesives, cladding, clinching. I'm not going to spend a lot of time walking through this, but this will be available online, this entire webinar, where you can go back to it as a reference. So here's some examples of what we gathered in the way of at least publicly known technology areas of focus and solutions that are being worked on. Some may already be in production, some may not in certain industries. We also included in this research quite a bit of information on what we knew about funded projects, especially if they were in the public domain. U.S. federal agencies, particularly the Department of Energy through the Vehicle Technology Office and otherwise, have been invested heavily in this as a way to support lightweighting to improve fuel economy here in the U.S. and across a wide variety of dissimilar material joining areas, as you can see here, and close to $20 million of funding. This may not be inclusive of all that's known and publicly funded today. And then obviously it's not just the Department of Energy, it's NASA, National Science Foundation, Army, Department of Defense, all have projects in this area. Many of them are in the automotive, aerospace, and defense sectors. There's also quite a few U.S. institutes like LIFT and others, national labs that have focused programs on this, and they're doing excellent work. Our academic institutions are leading the way as well in research on riveting, forming, welding, technologies that are focused on joining dissimilar materials. Some of these are federally funded projects, some are industry and or university internal funded projects. To show that this is not just a domestic issue and that it's really a global challenge for industry, there's more reference to major institute and university research programs that are being held in Europe as well as Canada. There's quite a bit going on in Asia too, but we did not focus our research in that area. Some of the more prominent industry players that have made known some of the industry applications that they're focused on for joining into dissimilar materials include the companies that are encapsulated on this chart. There's some really novel approaches here, not just for automotive, but aircraft, marine, and appliances, a wide variety of industry applications. Of the joining into dissimilar materials technologies that we researched, the most prominent that we could gather were focused on aluminum to steel applications, and that should be no surprise with a lot of them being in automotive and aerospace focused efforts. Here are some of the more prominent aluminum and steel joining dissimilar material technologies, and some of the companies and or universities, institutes that have ongoing efforts. As you'll notice here, there's quite a bit that is a combination of riveting and welding, which is in line with our technology solution as well. So let's transition to Optimal Process Technologies, our company, and the technologies we're developing and how we're trying to help solve that lightweighting challenge of joining dissimilar materials effectively and ensuring quality welds. Optimal Process Technologies is a spin-off of the University of Michigan. The technology was born there in partnership with automotive OEM, and Dr. Tae Kim, who you're going to be hearing from here in a little bit, was at the university at that time, helping develop these technologies and putting them into commercial use. The company itself had always had a focus on advanced manufacturing processes and lightweighting as its vision and mission. The technologies that we have unique intellectual property on include a hybrid joining process known as the rivet weld technology, where we have the ability in a one-step manufacturing process to both rivet and resistant spot weld in an effort to join dissimilar materials. And we can do this pretty effectively and have proven our ability to do it in a wide variety of material alloys and on different types of parts, sheet to sheet, sheet to casting, sheet to tube, for instance. We also have developed a rather unique machine learning weld quality assurance system that is particularly important for being able to measure in a highly automated environment a good weld versus a bad weld when welding dissimilar materials. Not only aluminums to steel, but aluminums to nickel and copper in the case of welding of battery tabs and tabs of batteries to bus bars. So the areas that we've been focusing on with the rivet weld technology has been in transportation applications. In automotive, it's been in the areas like I mentioned, where a number of automotive OEMs that we're working with are looking to swap out certain body in white related components from steel to aluminum or to another lighter weight material. And then they are faced in that particular case with trying to adjust their automotive body in white assembly plants to be able to effectively join those dissimilar materials on the plant in a very quick and efficient way and guaranteeing a very robust joint. As you can see here, an average body in white, you could have as many as 2,000 rivets. So guaranteeing good joining is very important to ensure quality of the product. The dissimilar material joining on a body in white, and we've seen this ourselves from benchmarking vehicles and teardown vehicles, that you actually can experience weld imperfections due to the brittleness, corrosion issues, various types of cracking and porosity that lead to catastrophic failure of those joints over time. We're also seeing this in our talk with aerospace OEMs that the joining of dissimilar aluminum alloys is a real need, whether it's 5,000 to 6,000 series aluminum alloys or 2,000 to 6,000. And those applications are all over an aircraft, from joining the fuselage skin to their supporting stringers or support structures throughout the vehicle. So there's also quite a bit of a need to join titanium to other materials, composites to other metals. So I'm going to turn this over now to Dr. Tae Kim as an inventor of the technology to explain a little bit how it works.
Hello, so this is Tae Kim. Yeah, it's my pleasure to have a chance to speak about our technology. So as you see here, so the overall concept of rivet weld is actually to take advantages from self-piercing riveting and resistant spot welding. So we do use rivets but rivet weld does not deform rivet like a self-piercing riveting. We do melt materials and create nuggets like a resistance spot welding. So let me try to explain more detailed process. In the figure, so there are two stack-up materials, top and bottom. Top is aluminum, and then bottom is high-strength steel, and then the nugget rivet is a steel. And the first step is to place the rivet on top material, and then apply welding force and welding current. This initial welding current can heat up the rivet and top material so that rivet can penetrate easily to the top material. Once the rivet reaches close to the bottom material, then trigger real higher welding current to accelerate the material heating and melting. Then nuggets start to grow up, and this nugget is actually a mixture of aluminum and steel. So nugget itself is intermetallic compound, and then this nugget is also encapsulated by the rivet and bottom materials. We can move to the next page. This is animation. Hopefully it can play well. Yeah, in this animation, we are showing the real application case. So once we create the conduction, and then we put feed rivet into the welding gun, and then process rivet weld. And since we are using low welding force, then does not require actually the two-sided weld. So once we put the weld conduction, then we can also do the one-sided welding, and then move to the next. So even we can do retrofitting the existing resistance spot welding robot gun, and then achieve this welding process. Also, since the rivet weld does not require, as I mentioned before, so we do not need a higher welding and clamping force like a conventional self-piercing riveting and the resistance spot welding, then one-sided welding is doable, as you see here. So with the sheet-to-sheet or tube and cathode parts, and then you see the welded sample. So in the top one, actually, we use the hot stamped steel as a bottom material. And also we highlighted here as an application point, weld point in automatic structure. So top one is roof rail to roof, and the second one is B-pillar, and then the bottom one is maybe shock tower to the outside the body enclosure. Right, okay. And here's more the technical detail. So you see here weld cross section, and then it's a lab shear test. So in resistance spot welding, when you do the dissimilar material with aluminum and steel, it can cause the interfacial failure due to the very thin layer of intermetallic compound. And then this interfacial failure mode is actually not prepared for the fatigue in the auto body. But rivet weld still, we pull out the older material, especially aluminum only, and then rivet and then bottom material still stick together, weld together. And you can see the left side of this slide as a cross-section image. And then, yeah, there is a real intermetallic compound as a nugget form. But this nugget, again, so is covered by rivet and the bottom material. And then nugget itself provides a really strong bonding force. And meanwhile, the outside covered melted part can provide a good fatigue performance. And we also compared this performance with the resistance spot welding and then self-piercing riveting. And then this rivet welded sample perform a lot better than two existing technologies.
And again, I think what's a real uniqueness about this is that you have a joint that can work, especially with very high strength stamped boron steels, which is a bit of a challenge. And you can create a very flush joint where the rivet head is very flush to the top material and doesn't protrude out of the back side of the joint, which is particularly important in some applications. And the fact that it's a one-step manufacturing process that can be performed in less than 1 second takt time.
Yep. Okay, let me continue about our second technology here, so which is a quality assurance system. Maybe then you're gonna.
Yeah. So our the other challenge that is out there is guaranteeing the quality of weld, as I mentioned, when you're welding dissimilar materials. So a big focus of the initial research that Tay was involved with at the University of Michigan, that now has proven commercially viable and is out in the market today, is weld quality assurance systems that particularly focus on measuring a good versus a bad weld, and when you're joining dissimilar materials, even if it's dissimilar alloys within the same class, like different aluminums, like we mentioned earlier. The focus of our research has been trying to put production quality systems that are in especially high volume applications that are very reliable and all type of welding applications, as you see here. Where we're finding the joining of dissimilar materials weld quality assurance being really important is in applications where yield rates are bad on welds, like in lithium-ion battery plants. Sometimes you have 10 to even north of 20% failure rate on welds, welding the cells tabs together as well as the tabs to the bus bar. Also applications where just the parts are too expensive to scrap are areas where weld quality assurance is particularly important. Example of a scrap battery cell, lithium-ion battery, would be as much as $5 depending on the amp hour format. And obviously areas where there's quite a bit of manual quality inspection labor that's needed. And we've found that in some applications, like battery welding, for instance, there's a large group of manual inspection people that are required to ensure that none of the product gets out there in the field that's bad. So, as you know, warranty and recall issues of any type of product, including a battery that goes bad, that goes into a vehicle, and then the vehicle fails to operate, can be catastrophic for a company. So basically, we're zero failure, and in other areas where market repair costs or line shutdown are far too cost prohibitive, are great applications for weld quality assurance systems in general. What we're finding is that weld quality assurance systems in the past haven't been overly reliable, especially where you can expect that the signals from those welding applications are going to be able to tell you pretty definitively if it's really a good weld versus a bad weld, to ensure that nothing comes off the production line without manual inspection labor. So that is the area of our kind of mission and vision, is to create these systems that are robust and effective. And we'll be able to prove this in a number of areas, including in ultrasonic welding for battery assembly, as I've mentioned. Tay, you want to talk a little bit more about this, our success here?
Yep. As Ben mentioned, not only myself, but also our core team members already have developed a quality monitoring system for the various welding applications. So for example here, so each welding process actually has a unique characteristics. That means that we can apply different sensors and then process information based on the weld type and application. But once the sensor signals and the process information were met, then the process to develop the quality monitoring system is pretty much identical as you see here. So we analyze the weld performance and then compare with the characteristics such as the metallurgical and then visual, and then do the signal process, because the raw sensor signal these days very high dimensional and then very large size data is not suitable for the real-time monitoring system. Then we extract the key numbers, key features, key values to utilize them as the input of our quality monitoring system, so that we can realize the real-time inline monitoring system. And now OPT, so we envision to develop and then commercialize a very intelligent quality assurance system for the various welding applications beyond this slide. To explain more details, I will example about the battery welding application. In battery cell module manufacturing, the most popular materials are pure copper, aluminum, and nickel. So those materials actually really highly electrically conductive materials, which is prepared for the battery application. But those materials are also highly the heat conductive materials, which is very bad for the welding application. Also, another issue, this is not a structural connection. This is electrical connection. That's why if there is any bad electrical connection between cells, actually battery pack module cannot deliver the design, the energy and power. Even further, the battery pack life cycle can be reduced because not well welded the module, and then other modules, they use more energy, more power than entire battery pack life cycle can be an issue. And this is the example for our monitoring system. So ultrasonic metal welding, this is one of popular methods for the lithium-ion pouch cells because the wider welding tab, battery cell tab can be joined by this process. Again, this is a solid state bonding, and then we apply sensors, so such as a microphone and power input sensor from the welding machine, as well as the displacement information between two tools. There are two tools, which is a hone and anvil to create the frictional welding. And once we measure these signals, and then, yeah, it's okay. Yeah. So in this slide, so we can explain, I can explain more. So those signals, LVDT, power, microphone. So once they are signal the process, and then we extract the only key features and then put into the monitoring system. But those sensor signals are very meaningful to explain about the welding process. And then our algorithm itself, so estimate the quality, either good, bad, or suspect weld. And then this slide actually can explain more about how you can apply this monitoring system in real plant. So once monitoring system estimates the quality of the weld or product, and then in inspection station, you can make a decision, the final decision, whether you're going to do the re-weld or really scrape them out. So that's the key. And then you can move to the previous slide.
Oh, sure.
And then the major reason why these sensor signal can represent the welding process. So in this slide, so the right side, we actually simulate about the contamination, the vibrational welding, and then surface contamination can explain about the process better. So black line on the right top graph, that's the two black lines are the normal from the two sensors, and then the blue and red are the abnormal cases which are contaminated. And then those signals can, even by looking at those signals, can match with the real weld characteristics. You can see. And then there is a problem weld interfaces. So using those signals, we were able to develop the monitoring system. Yeah, and so previous hour, the member also involved about the project, which is the University of Michigan, the research project to develop this monitoring system for the real application. And then the developed monitoring system was applied to the one of the OEM's battery assembly plant.
So I want to thank Tay and pause here to try to stay on schedule and leave some time for Q&A. So back to the lift staff.
Appreciate that. Thank you, Dan and Tay. A couple of questions that came in. Can you talk about the relative strength of the rivet weld versus the rivet only?
Oh, that's a good question. Actually, the rivet weld, this is a fusion welding, and then self-piercing riveting is the mechanical fastening and joining. The meaning of the quality strength is totally different because once you have a mechanical and fastening or joining, it will detach it to materials. But once you have a fusion welding, and then usually the welded part, their strength is higher than the base parent material. Yeah, that's why rivet weld, the strength is a lot better than any type of a mechanical and fastening solution.
Thank you. Another one that came in was, how does the energy requirement compare to resistance spot welding, percentage of resistance spot welding?
Actually, the real number is difficult to make an answer, but let me explain. Since we are increasing about the contact resistance, because when I have a higher contact resistance, and then I don't need to use a higher welding current, and then welding current just use a lower welding current. Usually the aluminum welding, so it requires really higher welding current. And also when I use a lower, I don't need a big power transformer. So that means reduce that transformer size and then reduce the energy consumption a lot. And I think it can be, it's close to the half of the energy consumption of the resistance spot welding when I simply compare with the welding current amount.
Which is important because it doesn't necessarily require a plant, like in the case of automotive assembly, to have to put a new transformer in. If anything, they're using less energy to answer the original question.
Yeah, also one more. So we don't need a higher welding force. That's why our welding gun size can be really small, right? And you don't need the heavy welding robot, right? Robot itself can be very small and then very cost effective. So that's why this rivet weld actually can enable the entire welding bonding, the assembly line as a cost-effective one.
Excellent, thank you. Let's see, a few more came in. How do you deal with the issues of intermetallic corrosions?
Well, so it's quite common that processes now have established specifications for coating the material before they're even joined, especially when you're doing dissimilar joining. But we take extra precautions with the rivet weld to pre-coat our rivets with a zinc metallic coating that protects the rivet, including in the process, and establishes a better bond with the material so it doesn't propagate into corrosion through galvanic reactions. So that's one measure that we take, but obviously we have to work pretty closely with our customers in the application to make sure that they're speccing the right material. We also have to take precaution in the rivet feeding and material handling systems to ensure that as well.
And does the rivet weld process provide a flush finish?
Yes, it does. We've been able to prove on a number of industry material samples the ability to maintain 1 millimeter or less protrusion of the rivet outside of the top material, and no protrusion out of the bottom side of the material, whether it's a sheet-to-sheet joint that we make or sheet-to-tube structure or casting. So very flush joint, which is particularly important in certain applications, like if you're going to join the A-pillar to a roof structure on a vehicle and you have to set on top of that, on top of the rivet, a windshield. It enables a very good form, fit, function joining application technology.
Okay, a few more. Since it is a fusion process between mixed alloy systems, have you looked into the long-term precipitation characteristics?
That is for the TIG or the real application? Yeah, actually, we are working with one of our potential customers, which is one of OEM. So to create about the guideline for this rivet weld performance. And then, yeah, once we have it, and then we can also share that data. But right now, so we are comparing with the resistance spot welding. But another issue to compare with the resistance spot welding, so it's very difficult to join the dissimilar material using resistance spot welding. That's why it's very difficult to compare the fatigue, because as I mentioned in the presentation, so the interfacial failure, yeah, and then once you have that, and then fatigue strength is really poor. But our process, since we are holding aluminum materials by creating nugget and then top rivets, the mechanical holding, yeah, the performance, I would say it can be really good.
And how does the rivet weld perform in fatigue loading? Is it better than resistance spot welding?
Yeah, especially for the dissimilar material joining. So our solution is actually targeting about the very challenging structure and then weld configuration, which is aluminum to really high strength steel materials or the really challenging weld point. We are not trying to replace the existing resistance spot welding for the steel to steel welding or aluminum to aluminum welding. So we are developing technology for the dissimilar material joining.
And we've made sure we've had testing on tensile shear strength testing of the joints we developed and compared that with industry standards for resistance spot welding to show the benefit of the rivet weld technology as being more robust.
Thank you. A few more before we want to be respectful of people's time. A couple questions about cost. Have you taken a look at the cost of self-piercing rivets?
Yeah, so actually the rivet shape and materials are pretty much close to the existing self-piercing rivet. Yeah, so cost-wise, the rivet cost-wise is same. Yeah, close. Yeah.
Yeah, so I think it's going to vary quite a bit from industry application to industry application. And obviously, the one nice thing about the rivet weld technology, aside from just rivet cost, SBR cost, is that we can often utilize the existing equipment that's already on the operation floor, existing weld guns. If anything, we can move to less expensive weld guns and less energy use, as we talked about. So for a new assembly plant, for a new vehicle platform, for instance, we believe we have a very cost-effective capital expenditure value proposition.
Along those lines, one more on the process. Is it handheld or does it require a stationary machine station? If it is handheld, can it be done horizontally and vertically?
So we obviously, when we prove this in the lab, the next step is to develop the more commercial-ready system, right? And one that, in the case we talked a lot about body and white assembly plant. So that required us to move to the next level of being able to put our rivet weld system on the end of a robot and being able to show that we can join at any orientation and within 1 second tack time. So we're working on with a couple OEMs right now to be able to prove that process out and show that's reliable and robust and doesn't need maintenance. And we're also even working on, with the hope of partnership with Lyft and a collaborative R&D project, an entirely indirect weld gun where we're doing a true one-sided joint where we don't need a backstop, where the backstop is in parallel with the electrode to make it even more efficient for a vehicle manufacturer to install on a line and be able to very quickly join dissimilar materials at any orientation quickly without having to worry about even where the backstop on a traditional C gun may be placed and cause difficulties with joining. Thank you very much.
We have just about reached our time today, but I want to thank Dan and Tay for their presentation this afternoon. If you have questions, Dan had his contact information up there. And if you have any further questions, you can always reach us at communications@lift.technology. I'd encourage everyone to join us next month as we tackle another lightweighting issue. Stay tuned for that announcement and who that speaker is going to be. And you can always keep track of who the upcoming speakers are at lift.technology/liftoff. With that, thank you very much, Dan and Tay. We certainly appreciate your time today, and thank you very much, everyone, for joining. We will see you next month.